Hi, this is Professor Jen-Mei Chan at Cal State Long Beach. In this video lesson today, we'll look at three root finding algorithms. They are Newton's method, secant method, and method of false position. We'll first derive Newton's method, which is the starting point for the other two methods, and look at some of the similarities and differences of those three methods. You may have first encountered Newton's method in one of your calculus courses. So that's where we're going to start. We're going to give a visual representation of Newton's method and look at its analytical derivations through Taylor's polynomial. Let's first start with a function f of x. We're interested in knowing where the root of f of x is. In this case, this is where the desired root should be. The way Newton's method works is to start with an initial estimate. The key, though, is that estimate cannot be too far away from the desired root location. And the function value of the initial estimate cannot be equal to 0 identically. Otherwise, you have already reached your desired root. The way Newton's method works is to draw a tangent line to the point x0, f of x0. And where this tangent line intersects with the x-axis becomes our next estimate of the root. We then repeat this process by drawing a tangent line at the point x1, f of x1. Where this tangent line intersects with the x-axis becomes our next estimate, x2. This process continues until some sort of a convergence criterion is met. Eventually, your estimates are going to be so close to the desired root, it is the desired root. To see why this visual representation works, we look at the following calculation. First, we look at the slope of the tangent line at the first initial estimate x0, f of x0. Recall from calculus, the slope of the tangent line is given by the first derivative evaluated at the point of tangency, which is f prime of x of 0. And that is given by the change in the y value over the change in the x value. Since the next estimate is obtained by assuming that its function value is at 0, because that's where the tangent line intersects with the x-axis, we have then f of x1 equals 0. With that, we have a simplified expression, x1 minus x0 equals the negative f of x1 over f of x0. After manipulating the terms, it gives us the expression for our next estimate, x1, which is x sub 0 minus f of x0 over f prime of x of 0. Assuming the denominator f prime of x sub 0 is not equal to 0, we can continue this process until convergence. Hence, we have the general expression of the following, where x sub n is the current term and x sub n plus 1 is the next estimate. This expression works for all n greater than or equal to 0. In particular, when n is equal to 0, that is your first initial estimate. Next, let's look at how Newton's method is derived from a theoretical point of view using Taylor's polynomial. Suppose that a function f is twice differentiable. This is what that notation means. C2 means twice differentiable on a continuous interval from a to b. Let p sub 0 be the initial estimates to the true root p so that the function evaluation at the initial estimate is not equal to 0. Now we need to require that because if the function evaluation at p sub 0 is already equal to 0, that means your desired root is already found. Then there's no need to go forward. We also need to assume that the difference between p and p0 is very small. This is to guarantee a convergence. If you start with a root that is too far, or start with initial estimate that is too far from the desired root, then it's very unlikely that it's going to converge. Now, if we consider the first Taylor polynomial for the function f of x expanded at the point p sub 0, then we get the following expression, We then further evaluate this expression at the point P. Basically plug in P wherever we see an x in that expression. We then get the following expression. Notice the c is any number in between P and P sub 0. Newton's method is a way to do a linear approximation. Notice that we draw a tangent line to the curve. It is in a way doing a linear approximation. So essentially we're looking at the linear portion of this expression, and the quadratic part right here gives the error of that approximation. Since the function value at the desired root P is equal to 0, we can then get a reduced expression as the following. We can further reduce this expression by assuming that the difference between P and our initial estimate P sub 0 is small. Now we want this to be as small as possible. That's why we want to choose an initial estimate that's close to the desired root. If we do that, then the term involving P minus P sub 0 squared is even smaller, so small that it's so close to 0. Therefore, we can assume that this term right here actually goes to 0. With that, we can write an approximated expression, which is 0 approximates f of P sub 0 plus f prime of P sub 0 times P minus P sub 0. It is this approximation because we're assuming that P minus P sub 0 is small, and we're also assuming that the expression P minus P sub 0 squared is equal to 0, while it in reality is not. If we then take this expression and solve for P, we get the following expression. And this expression gives rise to a way to calculate our next estimates P sub 1. The expression for getting the next estimates from Newton's method requires division by f prime of the root, the current roots. So we need to assume that the derivative evaluated at each estimated root is not equal to 0 before we can proceed forward. If that is established, then we have our general expression for finding the sequence of estimated roots from Newton's method, which is P sub n equals the P sub n minus 1, which is the previous estimates, minus f function value evaluated at the previous estimate, P sub n minus 1, and the derivative evaluated at the previous estimated root, f prime of P sub n minus 1. The natural question to ask yourself is whether or not this method would always provide a convergent result. It turns out that the method might be non-convergent at times, but in general, if you choose an estimated root or initial root to be as close as to the desired root as possible, then the algorithm would converge. Here's an example of something that might not be convergent, something that is flat. Say in this case we choose x sub 0 as the following point, and then draw a tangent line to the curve at x sub 0, comma, f of x sub 0. We can then get our next estimates as the following. We then draw a tangent line to the point x sub 1, f of x1. It may become quite apparent that the tangent line at x1, comma, f of x1 is quite far away from the desired root at this location. If we repeat this process back and forth, it's unlikely that this thing will ever converge. Next, let's look at how Newton's method is applied to a function f of x equals cosine x minus x equals 0. Notice that it is unlikely that you can solve for the x value by hand in this case. If we start with an initial estimate of pi over 4, which is this value right here in numerical estimation, and also notice that the derivative of the function is equal to negative sine x minus 1. Then the expression for P sub n is P sub n minus 1 minus the function value evaluated at P sub n minus 1 over f prime of P n minus 1, which corresponds to, for this function, P sub n minus 1 minus cosine evaluated at P sub n minus 1 minus p sub n minus 1, all divided by the negative sign evaluated at p sub n minus 1 minus 1. So if we now plug in p sub 0 equals pi over 4 with n equals 1, we would get p sub 1 to be pi over 4 minus cosine of pi over 4 minus pi over 4, all divided by the quantity negative sine pi over 4 minus 1. With the help of the calculator, it gives this value right here. For the next iteration, you would take this new value, p sub 1, and repeat the process for p sub 2. I wanted to make a note here how fast Newton's method actually converge. The highlighted roots right here coincides completely even after 3 iterations. This tells you how fast Newton's method converges. You can get to a result that is not changing only within the first few iterations. And this actually is one of the methods for the convergence criteria. If we notice that the updates are not changing much, then we know you probably have reached a desired root. Theorem 2.3.1 puts our heart at rest. This theorem basically guarantees convergence as long as some conditions are met. We start with the function that is twice differentiable. We assume that p is the desired root, and the derivative evaluated at p is not equal to 0. And the theorem says that there exists a delta such that the method converges and generates a sequence of estimates p sub n converging to the desired root p for any initial estimate p sub 0, as long as that estimate stays within a small range from the desired root p. So delta has to be small here in order for the theorem to converge, or the theorem to be established. Now here's a sketch of the proof. For those of you who are not math majors, I would just say that knowing this proof exists in the book is good enough. If you want to review it for yourself, go ahead. But if you're a math major, I would strongly encourage you to read through it and try to understand all parts of that proof. The proof basically goes as the following. We start with the function g of x, which is x minus f over x prime. We want to show that this function satisfies the two conditions in the fixed point theorem, because then it guarantees convergence. Once that's established, then the functional iteration defined from the fixed point theorem gives us the following. And like I said, the fixed point theorem basically guarantees convergence for any initial estimates as long as it's within a small range from p. Newton's method is actually a very popular method in optimization, because in the problem of optimization, we're always looking for either the maximum or the minimum. And we know from calculus that maximum or minimum typically occurs at critical points, and critical points has the characteristic of having the derivative equal to 0. So essentially finding where the derivatives equal to 0 gives rise to the maximum or minimum. But how do you actually find x value such that f prime is equal to 0? You apply Newton's method to f prime. That is to say, we can then find the estimates of the roots by applying this method to the f prime function. So instead of having just f on top, now is the f prime function evaluated at the estimates. And on the bottom, it's instead of just f prime, it's f double prime evaluated at the current roots. The root that you get from doing this will be the desired optimal point. Newton's method actually is very efficient for finding square root problem. For example, in this case, we wanted to find the square root of r for any real number r. What we do is we start with the function f of x, that is x squared minus r. Because if I do that, then I know the x value that solves this problem will be the square root of r. So to find square root of r, it's sufficient or equivalent to find a root to the function f of x described here. First, we notice that the derivative of f is simply 2x. So we applied Newton's method to this function here to get x sub n plus 1 equals x sub n minus the f of xn, which is just xn squared minus r divided by f prime of x sub n, which is just 2x sub n. If we clean this up a little bit by getting a common denominator, 2xn, then we get on top 2xn squared minus xn squared plus r, which then reduces to 1/2 quantity x sub m plus r over x sub n. For example, if we now want to find square root of 17, we want to start with a point that is relatively close to square root of 17. We know that 17 is in between 4 squared and 5 squared because it's between 16 and 25. It is actually closer to the 16 than to the 25, so we want to start with an estimate of 4. Then with the expression that we obtained earlier, we get x sub 1 equals 1/2 times 4 plus 17 over 4. With either calculator or by hand, you get a 4.12 from that. If we do this one more time, x sub 2 would then be 1/2 times quantity, 4.12 plus 17 over 4.12. Now with the calculator, you get 4.123106. If we do this one more time, we get x3 equals 1/2 times the previous root, 4.123106 plus 17 over the previous root, which gives us that big number. Just for the sake of argument, let's just do one more. Now that is a lot of numbers to write, but instead of actually writing out the calculations, you should pull out a calculator and type in square root of 17 just to see how many digits this estimate is accurate up to. Did you notice that it's actually accurate up to the 28 digits of square root of 17? This shows you how powerful Newton's method is and how fast the algorithm converges. And I want to make a remark here about how simple this method is. You might have learned about computing square root of a number in your previous math courses or encounters or experiences, but just to notice how easy this calculation was. You could have done this without any calculator if you didn't want it to, because everything here is a polynomial expression. Now, as simple as the method is to compute by hand, you probably wouldn't want to do this by hand anyways. This is where we need a computer to program it for us. In order for Newton's method to run, we need an initial estimate, x sub 0. We also need to make sure the program doesn't run forever, so we're going to need a maximum number of iteration, m. We also will need some sort of a machined 0 to tell the algorithm that when your convergence criteria is within a certain range, then the algorithm can stop. And that's going to be called TOL, the tolerance. We also need to have the input function f, as well as its derivative f prime. At the end of the program, it's going to produce the updated root. To save memory, we're going to denote the updated root as x sub 0 as well, because once the initial estimate is fed into the program, it's no longer needed. So we can replace its position with the updated root x sub 0. An optional output to have is the function value at the updated root. This is just a safeguard to make sure that you actually do have a 0 for your root. The first step of the program is to check the function value at the initial estimate. So let's compute v as the function value of x sub 0. If the function value is already within the tolerance of 0, then we can stop and return x sub 0 as the desired result. Otherwise, we're going to continue on through the iterations. Here we use the absolute value of the function value v because it could potentially produce a negative function value. If it's needed to enter through the algorithm, then we're going to iterate this through the Newton's iteration process up to m times, because m is the maximum number of iterations we're going to cap it at in order to prevent it from going into an infinite loop. Then each time in the iteration, we're going to compute the updated root as x sub 1 equals x sub 0 minus the f of x sub 0 over f prime of x sub 0 as described by the Newton's method. Once that's done, we're going to evaluate the function value at this updated root. Again, if the function value is already close enough to 0, then we would stop and return x sub 1 as the desired root. Or another way to just have a stopping criteria is to look at the differences between the updated root x sub 1 and the previous root x sub 0. If this stopping criteria is not met, we're just going to assign the updated root to what was calculated just now, which is x sub 1. This portion right here is together, and we can also end the for loop here as well. I want to make a remark that this is just a recipe for doing the programming. You can, of course, change the stopping criteria to anything that is appropriate. I'm just giving you an example of what could be done, and in your actual implementation of the Newton's method might look a little different from what I have here. Next, we look at an alternative way to do Newton's method, where it has the advantage of not having the function evaluations for f prime, but because it is approximation to the tangent using the secant, it is going to converge a little bit slower than Newton's method. So in the case of the secant method, we're basically replacing the f prime expression with the secant, and we know from calculus that secant is a very good approximation to the tangent as long as the nearby points are close together. If we now take the original Newton's iteration and replace where the f prime appears with the secant expression, we get this formula right here. Now notice there's a mistake on the n value here. It has to start with at least 2, because this method requires 2 initial points. So we need to have a previous knowledge on the m minus 2 term and the m minus 1 term in order to do the nth term approximation. That's why it needs to start with n equals greater than or equal to 2. A graphical illustration for the secant method goes like the following. Suppose for the function f of x, that is the desired root that we're interested in, we're going to start with the initial estimate of x sub 0, as well as another estimate of x1. We then draw a secant line between the points x sub 0, comma f of x is 0, and x sub 1, comma f of x1. The point where that secant line intersects the x-axis becomes our next estimate, x sub 2. We repeat the process by drawing the secant line between the point x sub 1, comma f of x1, and x sub 2, comma f of x2. The point where that secant line intersects the x-axis becomes x3, which is so close to a root of the function right there. Although we started by trying to look for a root over here on the left hand side, we ended up getting a root that's on the right, and that's okay. It happens. And the problem of that the fact that we actually got a different root than we originally intended, was because we chose an initial estimate that is way too far from the desired root location. In the pseudocode for the secant method, we require 2 initial estimates. And again, the maximum number of iteration, m, a machine 0, which is epsilon, as well as the original function f. The desired output is going to be the root p. For the simplicity of the notation, let's let q sub 0 be the function value at p sub 0 and q sub 1 be the function value at p sub 1. As long as the iteration is less than the number of less than or equal to the maximum number of iteration, we're going to go through the secant method estimate to produce the update p. If the update p is relatively close to the previous estimate p sub 1, and that's what this means, it's that their difference is really small, so small that it's close to 0, then we're going to stop and output the desired root p. Otherwise, we're going to go through the iteration one more time, but before you go through it, you need to do an update of just basically a change of variables so everything can still make sense. So we're replacing the p sub 0 in this equation here with the new calculated root p sub 1. We're replacing the function value of p sub 0 with the function value on the new p sub 1. And the p sub 1 now becomes the updated p, and q sub 1 becomes the function value of the updated p. Once the change of variables is defined here appropriately, and we go through this calculation one more time, everything would make sense. You basically repeat this process until the convergence criteria is met. The next method is called the method of false position, and that's just an alternative way of secant method. It basically does exactly the same thing, except it forces the endpoints to bracket a root. Let's look at this through a graphical example. On the left here we have the method of secant, and on the right here we have the method of false position with exactly the same function f, with exactly the same initial estimate of x sub 0. Let's start with the secant method here. With the next estimate root x1, we can create a secant vector between those 2 points, and that gives us this next estimate of x sub 2. We can then create the secant vector between a secant line between those 2 points x2 and x1, which then gives us our next estimate x3. Notice that in between the estimate x2 and x3, the desired root, which is located right there, is to the right of that entire interval. Therefore, x2 and x3 does not bracket the desired root. The secant method doesn't really care about whether or not it brackets a root. To continue, it would then create a secant between x2 and x3, which is about right there, and then get our next estimate x4. On the other hand, the method of false position would do something different. Because x3 and x2 are both on the left side of the desired root, which doesn't bracket the root, we're going to choose instead x3 and x1 for our next iteration. And if we do that, we get the secant line between x3 and x1 to be like that. Notice that it actually gets to our desired root a little bit faster than the secant method. A couple remarks about the method of false position is that it is actually not used often in practice because it is an extra condition to check, which you really don't gain a lot from that in terms of speed. So that is why it's seldomly used. A secant method, which has a superlinear convergence rate, converges faster than the bisection method, but its convergence rate is worse than the Newton's method. So for that reason, Newton's method is typically the priority, and if the derivative evaluation becomes an issue, the secant method gets to be used. The pseudocode for the method of false position is fairly identical to the pseudocode for secant method, except there's one new step in step 6 for checking whether or not the estimates bracket a root. Once the two estimates are calculated, in step 6 is checking to see if the function value of the two previous estimated roots is less than 0 in its product. If it is the case, that means it actually brackets a root. If it brackets the root, like in this case, Then we do a change of variable before we go to the next step. In the previous step, x1 and x2 are your left and right roots. In the change of variable, you're going to assign x1 to the x of 0 in the previous calculation. You're going to assign x2 to the x of 1 in the previous calculation. And that is what this step right here does. If that's not the case, and then we go to step 7, which means that the two roots actually do not bracket a root. In this case, x sub 0 stays the same, and x1 gets to be assigned to the x star that was previously calculated. And then once you have this initialization set up, or a reassignment set up, then you can go through the loop until it converges. This video now is concluded on our discussion of Newton's method, a method false position, and also the secant method.